Okay, acceleration time graphs use the same concepts in the speed time graph or a velocity time graph or a displacement time graph. Okay, two things we need to consider. We'll look at the area under the graph and we'll look at the gradient. Okay, there's two kind of things to cover. The area under the graph is the change in velocity. Okay, so area under the graph for this one, we've got an object moving at 5 meters per second squared with an acceleration of 5 meters per second squared over 80 seconds. Okay, the area under that graph is that rectangle there. And if we consider what it is we're measuring, if we do a bit of a dimensional analysis, as it were, we've got our time multiplied by our acceleration. Think of the units, okay? We've got seconds multiplied by meters per second squared. Okay, that's seconds and that one. So we're left with meters per second times 1, which is velocity. Okay, so the area under the graph is the change in velocity. Right, let's look at the gradient. In this one, we've got a flat line, horizontal line, so that means we've got a constant acceleration. Okay, at this stage in the course, we deal with constant acceleration. Okay, so that line will always be horizontal. Just as an aside, roller coaster design will take into account non-constant acceleration. They call it jolt or jerk, and if you imagine yourself on a roller coaster, you can kind of see the change in acceleration is important for making the ride exciting. Right, so constant acceleration, horizontal lines. All right. Now, let's have a look at this one and just kind of describe what's going on. We have got up here, okay, something moving with a constant acceleration, gradient is 0, constant acceleration of 5 meters per second squared, okay, for 40 seconds. Now, we've got a discontinuity here. Okay, we don't draw anything between there and there because we're modelling the situation here. We're saying that at 40 seconds from the moment it starts with this acceleration, it's suddenly going to have 0 acceleration. So the acceleration, change in acceleration is instantaneous. Now that's a modelling feature. It has its limitations. Okay, but for the moment, we just need to be aware that this instantaneous change in acceleration is what we're dealing with. Okay, so after it's accelerated 5 meters per second squared for 40 seconds, it suddenly has a 0 acceleration. So what does that actually mean? Okay, if it's got 0 acceleration, that means we've got a constant speed, or let's call it velocity. Okay, it's got a constant velocity. If we think of a velocity time graph, okay, the gradient of that gives us our acceleration. If our acceleration is 0, okay, we will get a horizontal line on our velocity time graph, and that means we've got a constant velocity. Okay, so that's 0 acceleration for 20 seconds. Right, this bottom one here. Now, we've got an acceleration of -5. Right, some other words that we could use for this, okay? We could say we've got a deceleration, only one L in there, and 2 C's, sorry, my spelling. We've got a deceleration of 5, okay? We could say we've got a retardation of 5, okay? Or we could say our acceleration is -5. Okay, so these are all the different things, and that happens for 20 seconds. Okay, so the important thing to note is these jumps, okay, these instantaneous changes of acceleration, and that when we've got a 0 acceleration, we've got a constant velocity. All right, let's have a look at an example now. Right, a car accelerates uniformly at 5 meters per second from rest for 20 seconds. It then travels at a constant speed for the next 40 seconds, then decelerates uniformly for the final 20 seconds until it is at rest again. Right, we need to draw an acceleration time graph for this information. So what are the important parts that we need to know? Let's get a yellow. Right, it's this bit. Accelerate uniformly. Okay, and at 5 meters per second square from rest. Okay, anything mechanics, remember, rest is u equals 0, starting point. And we've got a time. Okay, so that's our first bit. That's the first bit on our graph. Okay, right, the second bit of information we've got is it travels at a constant speed for the next 40 seconds. Okay, that's the next bit we're looking at. And then finally, it decelerates uniformly for the final 20 seconds until it is at rest again. So all that bit is the third bit. So our graph is going to be broken up into 3 bits. Okay, we've also got to draw a distance time graph. Right, here's our acceleration time graph axes. Okay, there's our 5 for acceleration. Right, so there's the first bit, 5 meters per second squared for 20 seconds. Now, it travels at a constant speed. Remember that constant speed there is our velocity, acceleration equals 0. So that's that bit there. Then we've got our decelerate. Remember, deceleration, retardation is an acceleration with a negative value. So we've got -5 there. And that's for 20 seconds. Okay. And again, just a reminder, we've assumed that the rate of acceleration jumps between different rates. Okay, it's instantaneous. Okay, let's have a think of our distance time graph now. So what's actually happening? We know we're starting from 0. We know that our acceleration is uniform. Now, if our acceleration is uniform, okay, what does that mean about our velocity? Just have a little think. Okay, we can look at it with the numbers. Our u is 0. Our acceleration is 5. The distance is what we're looking for. Okay, and what else do we know? We know time is 20 seconds. Now we can use s equals ut plus a half at squared. Now, if we haven't covered this bit yet, don't worry. This bit will be 0. So we've got s equals a half times a t squared. So our distance is going to be related to t squared. Okay, so it's going to be a parabola. It's going to be one of those nice curve shapes, like that. Okay, and it's going to be this little bit here. All right, we've got s as a function of t squared. Okay, so that tells us it's not going to be a straight line. Okay, we're going to get this little bit here. We've got, where's my pen? There we go. We've got 0 to 20 is our little parabola shape. We think as our acceleration increases, okay, the acceleration is our rate at which our velocity changes. So the rate at which our velocity changes gets bigger. Okay, so the distance away from the starting point will increase. It will start off slowly, less distance, but then that distance will increase more as we get towards 20. Okay, now this bit between 20 and 60, we've got a constant speed. Alright, that's a constant speed bit there. Alright, so if it's going at a constant speed, the distance it's travelling will be a straight line. Okay, because speed is distance over time, so for every unit of time it'll go up the same amount of distance. Okay, that's the gradient. Alright, so that's our constant speed there. Now this last little bit is kind of this bit in reverse, isn't it? It decelerates again until it's rest, till it stops moving. Alright, So its deceleration affects its velocity in the same way that this one has. Okay, so that's what it says here. As the speed increases, the curve gets steeper, but with a constant speed, the curve is straight. Finally, the curve gets less steep as the deceleration takes place. Okay. Right, a reminder of distance-time graphs, acceleration graphs and velocity graphs. They will usually all be linked together. Okay, you'll have two graphs to draw, one of which will inform the next one.